Today, I'm going to present one of the greedy technique, the Dijkstra's algorithm, considering the single source shortest path problem. Without so much further ado, I'll start my discussion with this example of a network A, B, C, D, and E. So we have here 5 nodes from node A to E. As you can see, we have here weights of every edge. So we have 3, 7, 2, 4, 5, 4, and 6. All are positive because Dijkstra's algorithm does not work on graphs with negative weights or edges. To start, let's set the distance to source vertex as 0 and set all other distances to infinity, as we can see here in Dijkstra's algorithm. For every vertex set to infinity and its penultimate vertex null, and the source distance is 0. Below are the 3 vertices and its remaining vertices. To start the computation, let's start from the source A, where its distance is set to 0. And we will have here A, that is our starting source, and its distance is 0. Then relax all vertices adjacent to the current vertex. So we have here A adjacent to B. So the edge of A to B is 3, and 3 is less than infinity, and we update the distance of B to 3. Next, we have A adjacent to D, and the edge of A to D is 7. And 7 is less than infinity, then we will update the distance of D to 7. Let's copy the other remaining vertices. So we have here C, that is unvisited node, and its distance is infinity, and E, also unvisited node, and that distance is infinity. As we notice that A to D is greater than the length or the weight of A to B, we disregard the weight A to D. Node A has a visited node, and let's move to the node B. Then the distance of B is equal to 3, that is adjacent to A. Then relax all the vertices adjacent to the current vertex, and we have B to C. So the weight of B to C is 4, and 4 plus 3 is equal to 7. And 7 is less than the distance of C, that is infinity, so we update here the distance to 7. Then we will write here C adjacent to B, and its weight or distance is 7. Then next adjacent to B is D, and its weight costs 2. Then the distance of B that is adjacent to A is 3, so 3 plus 2 is equal to 5. 5 is less than 7, so we update the distance of D to 5. There is no other adjacent to B, then let's copy the node E, that is unvisited, and its distance is infinity. Node B as a visited node, and we move to node D. Then relax all vertices adjacent to the current vertex. To write in 3 vertices, we have D that is adjacent to B, and its distance is 5. Then we have D adjacent to C, and its edge is 5. So we have 5 plus 5, that is equal to 10. And we will disregard this one because we have the way D to E, which has a shorter length or smaller cost. That is 5 plus 4 is equal to 9. To write it in vertices, we have E that is adjacent to D, and the distance is 9. The distance of E is already been updated. Then we copy the other remaining vertex, that is C, and adjacent to B, and its distance is 7. Node D as a visited node. Let's move to node C. C has a current distance of 7. To write in 3 vertices, we have C that is adjacent to B, and its distance is 7. The way C to E has an edge of 6, and its current distance is 7. So 7 plus 6 is equal to 13. Since the distance is greater than the distance of E, no weights are updated. Then we copy the other remaining vertex, that is E, and it is adjacent to D, and its distance is 9. Since C to E has a greater weight than the way D to E. Node C as a visited node, then we move to node E. Since node E is the endpoint, we write it in 3 vertices E that is adjacent to D, and its distance is 9. And we mark it as a visited node. To summarize, from node A to node B, we have the length of 3. And from A, B to D, we have the length of 5. Then from node A, B, and C, we have the length of 7. And from node A, B, D, and E, it has the length of 9. Here is the algorithm, and the time efficiency of Dijkstra's algorithm depends on the data structure used for implementing the priority queue and for presenting an input graph itself. We can see that the shortest path from node A to node E is through node B and node D, with a total distance of 9. The time complexity for the algorithm for graphs represented by their adjacency list and the priority queue implemented as a min heap, it is in O magnitude of E log magnitude of V, or we can say O E log B, where E is the edges connected to each node and B is the number of the nodes. This ends my presentation in Dijkstra's algorithm. I hope you learned something.